All right. What else? Screen. All right. How's everyone going? Going good? Yeah. So we're approaching the end of the course, and yeah, so we're moving on to particle kinetics, starting from this lesson, and we'll be doing more methods on the Monday next week before moving on to rigid bodies, which will bring us into the term. So yeah, rigid body kinematics should be on Wednesday next week, and then rigid body kinetics should be Friday, so the last lesson. So yeah, so in today's workshop, I've decided to bring quizzes back. So that'll be good for hopefully being able to interact with the small, because this is a bit of a lecture style workshop, I guess. I don't know, just like the way that decided to run it. But yeah, hopefully that'll be a bit more interactive. But I've decided to hold off on that until I talk about pulleys and spring extension first. So yeah, without further ado, we'll just get started. I'm going to quickly check if there's any problems. No one's saying anything. Seems like I'm sharing screen. All good. All right. So pulleys, right, is something that's been in the course since pretty much the first lesson. They're like these things. I'll just roughly draw it. They look kind of like that, right? And yeah, there's rope attached to them, and yeah, it's something that we've talked about, but we haven't really explained fully. And yeah, and I feel like this is the best lesson to talk about them, because we're going to be using them a lot in the next few lessons. So I'm just going to rub out this, because I've got an organized way of presenting what I want to say. So with pulleys, you might have seen in the lecture today, the main assumption that we have of them is that they're massless and frictionless. So this will help with our calculations. But I think more importantly, something which I never really was able to put into words, but it's something that you should intuitively understand about pulleys. A rule of thumb is that the tension is consistent throughout each rope, right? So I'll show you a few examples of what I mean shortly, but you just have to know that if we have a rope, so we have a pulley, right? Like that, you're never going to have the case where one part of the rope has more tension than another part of the rope. You know, the tension is going to be the same between both ends, okay? And I'll tell you how the maths works out on that very shortly. So basically, the first type of pulley there is a fixed pulley. There's a few names for this, but you can call them fixed pulleys. People know what I'm talking about. And the next one is movable pulleys. Okay, so here's the two types. And mathematically and physically, we have to think about these two things quite differently, even though they're both pulleys, right? So I'll draw an example of what I mean for both of them. Pretty much what I just drew above for this fixed pulley, right? Okay. I'll draw the next one as well, just to contrast them. Okay. Pretty much, the difference is that fixed pulleys will have this hidden reaction force, right? You can think of it like a pin support. right? And that's how the maths will work out when you're analyzing the free body diagram. So if this was a cut of a free body diagram, right, you might be thinking about, okay, well, how did both of these directions equal t? You know, because like mathematically I'm looking at it and like these are pointing in different directions, so how can they both be the same thing? Well, that's because the reaction force will counteract whatever, such that the maths will work out, right? I'm going to butcher the direction here, but it could be something like that as the net reaction force. Yeah. Is there something going on? Check the chat. Looking okay. All right. Nextly, there's movable ones. So yeah, again, this is a free body diagram cut of a pulley which is subject to moving up and down, for example, right? And for these ones, you can like sum the forces. So in this case, we'll do sum of the forces in the y direction. Well, okay. We'll say there's no acceleration, right? So if it's in static equilibrium, in this case, we'll find, if we call each of, in the rope which wraps around like this, so this is the same rope, we can call that T for the force in that rope. And because of how we're analyzing the forces, this will be 2T, right? So note, if this is rope 1, if this is rope 1 here, and this is rope 2, well, we have two different ropes, right? Which is why we're allowed to have a different tension, right? Yep. You can also call this T if you want to call the tension in this rope T, but then each of these will be 0.5 T. It's the same thing, right? You're just solving for some unknown T, which is proportional to some degree, right? Yeah, I'm actually going to talk about this point I have at the bottom here first. So motorized. So I've seen like one question. I haven't included it in this lesson's workshops, but I've seen one question for motorized pulley, but it might look something like this, right? And that moment that's being applied through mechanical energy, mechanical something, yeah, the motor pretty much, right? It's going to be proportional to the tension in the rope, right, multiplied by the radius. And this should make sense given what we know about how moments are forces multiplied by the lever arm, right? So the radius is basically the lever arm. So, I mean, this equation, not in the context of motorized pulleys, this equation will come up a bit when we're analyzing rigid bodies because, yeah, we might analyze some rigid bodies which are circles, right? Like a 2D circle, and you might see something similar, just not in the context of a pulley, right? Yeah. Or maybe in the... Yeah, okay, we'll see when we get to rigid bodies pretty much. I haven't looked at enough examples to make like these general claims at the moment. Okay, so next I want to talk about mechanical advantage. Does anyone in the room do mech-eng or anything? Yeah, maybe some people. So you'll find in your degree there's a few types of components, or maybe machines they're called, which can give you a mechanical advantage. One is like a lever, right? Another is gears. And the last is pulleys, right? So pulleys will generate like a mechanical advantage for you, which I'll explain down below. But in general, there's this balance between force and displacement. Okay. Yeah. So I'll show you some examples first. So here's a pulley, fixed pulley, right? And there's this rope which goes around here like this. And on one end of the rope, we have a box which is like 100 kilos, for example. And it's like, okay, how much force do we need to pull this box up, right? So if you analyze, if you do your like some of the forces and stuff, you'll find that, well, actually, not some of the forces. You'll just know pretty much that this force will be equivalent to the tension, right? Which is going to just be mg. And in this example, we have a mechanical advantage of only 1. Okay. So all the pulley is really doing here is you can redirect the angle which you're pulling this box, which might be convenient or whatever, but it's not generating any sort of mechanical advantage. However, in this scenario, right, so we have a rope that's fixed to the wall or something, and it's attached to this moving pulley, and then this is a fixed pulley this way, right? So in this system, because we have a moving pulley, and because we have 2 different ropes, you'll find that when we're analyzing this moving pulley, yeah, basically this, right? I'll just write out what my notes say first. You can allow for mechanical advantage of 2, right? Such that the force that you have to pull on this rope is only going to be half as much as with the previous system, right? So like, in terms of conservation of something, in terms of some sort of conservation, how can this be possible? Well, it's because we have to trade off displacement, right? So essentially, the rope must be pulled twice the distance to account for, so here it has to be pulled twice the distance as over here. Right, so that whole moving pulley is moving the same displacement. So yeah, for each 2 meters of the part that I've highlighted in orange, you pull 1 meter for the part I've highlighted in blue, pretty much. Right? Yep, and so when you do enough of these questions, hopefully you'll develop like a pretty intuitive understanding of this. Because honestly, it's like kind of abstract. Like I'm struggling to even like describe what I'm talking about a little bit, but I feel like when you do the questions, yeah, hopefully it just makes more sense, right? Yeah. But do we have any questions in person? No. No. Okay. Check on Teams as well. All looking good. All right. Usually when there's no questions, it means that I'm explaining things well, or I'm explaining things so badly that like people don't know where to even begin asking questions. So hopefully it's not the second case. All right. Oh, here we go. So here's a more complicated system, and yeah. So first, I want you to look at this and spot which ones are moving pulleys and which ones are fixed pulleys, right? And the second thing I want you to do is think about think about this box moving downwards, for example, right? How is that going to affect each length of rope? Which ones are going to stay the same and which ones will be variable, right? Because this is one of the extra questions that are provided, right? And yeah, you'll see. So basically, right, because, actually, wait, so this is a moving pulley. This is a moving pulley, right? The other three are actually fixed. There's some sort of thing fixing these down, right? And so the moving part for A, we can just call here, only this part of the rope will move, right? Like all of the rope will technically move, but this distance will change, right? Same with between here and here. That part will move, but this part will stay the same. And even this distance from here to here will stay the same, right? Yeah, so it's just like thinking about the distance of the pulleys from each other, right? That's one thing you want to do. Yep. So LA and LB will not be fixed in place, right? So the total length, yep. So the total length of the rope, right, that we're thinking of, is going to be this. Because we've got 2 pieces of rope, 3 pieces of rope here, right? And so the total length of the rope is going to be 2 lots of LA plus 3 lots of LB plus LO, which is going to be some fixed distance, right? Which won't move, right? I haven't represented it here because it's just like, it's just some, it's just everything else, right? Like all the rest of the rope, which hasn't been measured, I guess, like on my little diagram. Yep. Hopefully this sort of makes sense. Does anyone have questions about this? Okay. Cool. So I'm going to move on to this question, which was actually one of the extra practice questions which I provided on Wednesday. But I've noticed that it's included as one of the workshop questions. So we're just going to run through it now because there's a few concepts from here to do with like friction, which is good to revise for kinetics as well, because kinetics will still involve friction. Okay, so firstly, like we talked about, there's a pulley in here. There's a fixed pulley right there. And actually there's also a moving pulley. It's just attached to the box, right? So what's going to happen is that we don't need to analyze this fixed pulley, because if we analyze a fixed pulley, right, where this is all the same piece of rope, right, that's wrapping around. Wraps around like that, okay? We're not really achieving anything by analyzing this because we're just going to be solving for whatever reaction force causes this to not move. And then, yeah, there'll be some sort of reaction, right? But that's not useful for us because that's not what the question's asking. So basically we actually want to be, actually, you know what, in case anyone wanted to copy that down, I'll leave that in the corner. Yeah, what we want to be doing is analyzing the free body diagram at the box, right, with the moving pulley. So what that'll look like is this. Alright, I'm going to start with the moving pulley. So this is the same piece of rope, right? Wrapping around like this. Therefore, it's going to have the same tension, right? And that's going to be 100 newtons. So that's good. And yeah, and we also put in the normal force, which is acting on it. And we also put in gravity. Oh, sorry, the weight force. It's 40 kilos. Right? And we include friction. So when I write FF, the way that I like to do it is FF represents the direction of both static and kinetic, kinetic friction, right? But what we do when we're given both values is, both values here of static and kinetic friction, is we always have to start by assuming that the box doesn't move, unless the question explicitly tells you that the box is like it's moving or whatever, right? So we assume, start by assuming static, right? Okay. But first, the way that we always solve for friction, right? You go from weight force to normal force to friction, right? In that order, right? For static friction. So we're going to start with some of the forces in the y direction. So is this box accelerating up and downwards? It's not being yanked, so no. So the up and downwards forces should balance each other out, basically, right? These are at a 30-degree angle from the horizontal. So that's the weight force. That's 2 lots of the tension force. And we're solving for n, which is normal force, right? So now that we have the normal force, we can, we can calculate, actually, well, what we'll do, right, is we'll do this. We're gonna follow our assumption that the box is static, okay? So we go this. Okay. So 2 lots of the tension force in the x direction. And here we have FF, right, which is like our unknown friction force, which we can solve for. Okay. So now we have to compare that to our static friction threshold. Okay. Which I'm calling FS. Let's call it FS max. So this is the one which requires the normal force in the equation, right? The other one's the unknown that you're solving for. So we plug in 0.5, which was our static constant, multiplied by n, which we solved for. Okay. Yeah, if this stuff's not making sense, I'll draw out the graph shortly, right? But essentially that's our threshold. So if our calculated friction is greater than, yeah? Right, all good. So yeah, think about, we're going to be comparing FF with FS max. So if FF is under FS max, right, then we're using static friction. But if FF is greater than FS max, we have to use kinetic friction, right? And that's the case here. We use kinetic friction, and we use FK in our calcs, right, which we have to calculate. So basically this means the box is moving, right? It's able to overcome the static friction, and now we just calculate the acceleration of the box with respect to this constant kinetic friction that it's experiencing as well, right? F is ma, right? In the horizontal direction. So that's the 2 lots of the tension horizontal component. The mass was 40 for the box. This whole part is equal to 173.2. And this has this formula. 0.4 was the kinetic friction constant that we were given in the question. And n was still the n that we calculated for normal force. Right? So the unknown that we're solving for is A. It's moving to the right. Yeah. So basically, with friction, you can always think of it in terms of a graph. So friction force on the y-intercept, and then intercept axis, and then F applied, so like force that you're applying, which would be like the pulling force, I guess, in the horizontal direction on the x-axis, right? It looks something like this. Where as this is going up, use static friction, right? Sorry. So you can solve for that. And this one is Fs max, which is this. And this one is Fk, which is this. Right? Yeah. Right. All good? Any questions? Check online. Right, so that was the first question. We're going to go through a bit more theory, and then I'll chuck the quizzes at you, and then we'll have our break where I'll take attendance, right? Okay, so springs, right? I don't know if springs have popped up earlier in the course before this, but you'll definitely start seeing them in kinetics for particles and for rigid body kinetics later as well. So springs are similar to ropes in terms of it's like a line, right? But with springs, you can pull them and you can compress them as well. You can imagine it as something which is like made out of steel, for example, right? Material-wise, right? And as such, one thing to know about it is it has this stiffness property. Yeah, so for example, something which looks like this. Which is a material property. All right, has anyone in the room done Maths 1101, material science course for engineering? Yeah, maybe some people online have as well. But pretty much, this is the 1D version of elastic modulus. Right, and I say you can think of springs as made out of steel because we assume that they have uniform properties in tension and compression, right? Similar to steel. In other words, yeah, this stiffness is going to allow for like proportional stress strain, force displacement, whether in tension or compression, right? But yeah, actually, I think I'm tangenting a bit. But yeah, so that just keep in mind, like spring stiffness is a material property, pretty much, right? The other thing to note is that you have to keep in mind the unstretched length, right? Which we can denote with LO, for example, of a spring, because if you think about it, right? Imagine you have a spring in your hand, and you stretch it, and it gets harder and harder to pull, right? And same with compression. It gets harder and harder to push together. And so that unstretched length is pretty significant because that's like where that's going to have the least resistance, right? And you'll see like in the calculations how this will actually affect things. There's two formulas for springs in this course. I don't think we've seen a Hooke's law question, but I'll just chuck it in here anyway. Right, but yeah, in this topic you'll see spring energy pop up a lot. And the formula can look like that, right? This is part of where I'm going to be going with work energy, the work energy equation. This will slot into it pretty much. But essentially, yeah. When we're talking about these delta L's, these are the definitions for them that I've included. So basically delta L is the deformation of the spring, right? So whatever length that you're at minus whatever original length that you had. Sometimes I just get lazy and instead of writing delta L, I'll just call it X. And similar for delta LA, I just might call it XA. But yeah, what's important to note is that X denotes like this deformation, or like it's the difference between two numbers, right? Even though it's not like a delta in front of it. So just keep that in mind whenever you see an X in the formula, right? It's just like a different notation. Yeah, I'll leave this up for a second so everyone can copy this down. And I might just check online how everyone's going. Doesn't seem to be any questions online. So, okay. That leads me on to work energy. So that's kind of like the big topic this week. And yeah, I've alluded to it before, but in the mech school they call this the Holy Grail equation, because you use it for every question in this topic. Yeah, so on the left here, we have the work done from A to B. That's what this notation stands for. Here we have the change in kinetic energy. Here we have the change. Oh, sorry, I went right change. We have the change in gravitational potential energy. And spring potential energy. Right? And usually I'm a bit lazy with writing this out fully, because what I like to do in this equation is I like to write W from A to B to denote that I'm talking about, yeah, like the difference in work between scenario A and scenario B, or like positions A, position B. But technically all of these should have A to B as well, if that's the case. But I don't know, to me it's just like kind of implied if you've included it like for the W. So, but yeah, that's like the full thing technically, right? Yeah, so for the first component of this, it's the work, right? And here I've included the the integration formula, but usually that's not required in this topic. You can use this version of it, which is basically, this is the change in displacement from A to B, right? And F denotes the external force to the system. So in the examples that you'll see later in this workshop, I think all the examples have some sort of change in work, right? But for a lot of the questions which I've included for practice, there's no change in work. The entire system is made up of kinetic energy, gravitational potential energy, and spring potential energy, right? So you have to watch out for cases where there's actually no work, right? You just have to be able to recognize it. And here's the cases which I've listed. I mean, so far I've only seen these two cases before, right? External force being added to a system through someone pulling on a rope, for example. This will add energy to your system, right? And friction, right? So this does the opposite, pretty much. It removes energy. Right? And what we consider as S, they're both, it's like displacement in both cases, but when someone's pulling on a rope, you have to be careful of the perspective that you're thinking of in terms of S. So that, in that case, the S is actually the rope, the amount the rope moves, okay? Which sounds obvious, but I'll show you why later. That might be a bit confusing, okay? Next we have delta T. Delta T denotes the kinetic energy in the system, where V is your velocity, right? Yeah, you'll probably remember this from either high school physics or physics 1A. That's your kinetic energy, right? So we've kind of just, now we have the change in kinetic energy pretty much. So that's going to be this formula, essentially. Next we have the change in gravitational potential energy, where H is your height. this is pretty much just your change of height, but depending on where you set your datum, yeah, just keep in mind that each of these values could be negative, right? So HA or HB or whatever, they can be negative numbers. So if for example, you go from A over here at this height, and you set that as your datum, and you go down to B, then this height of B is going to be some negative number, right? If you go down from your datum. And lastly, we have the change in elastic energy. So yeah, that's kind of what I was talking about earlier. Here I've done it in delta L notation, but this could be seen as, could have this as xb squared minus xa squared, and it would mean the same thing, right? Just keep in mind, it's not this. Okay, it's this. You end up with different numbers, right? Okay, so I've done a lot of talking. I'm gonna go over to quizzes. Well, I'm gonna check the chat first. Are these symbols for kinetic energy, potential energy, and spring energy conventional in engineering? It's a good question. I don't want to make like a sweeping statement, but I've seen this in the mech school being taught, and I've seen this in the mining school in the lectures. So I assume that, yeah, because I don't know, like in high school, I called kinetic energy KE. I called gravitational potential energy GPE, whatever, right? You might have seen those as well, but I guess at least in 1300, this is what you're taught, and maybe that's the case moving forward as well. I'm not too sure. Yeah. Yeah. U for potential energy in physics, yeah, like in gravitational potential energy for like an astronaut, like above planet Earth or something. I think you see U. Yeah, I'm not sure what the convention is, to be honest. Yeah. Okay, so we'll move on to quizzes. I'm going to show the QR code. Oh, show QR code. Yeah, so if everyone can join this, I've just lined up a couple of questions to do with what I've just been talking about, to see if you have a good understanding of these two topics. What was I talking about? The pulleys and the springs mainly, right? Because this will be very important for the next few questions. If your like physical understanding of it is good, the maths isn't that hard, to be honest. Like you should be able to work out the maths. It's just like rearranging a formula over and over again. But you just have to make sure that your understanding of the pulleys and the springs are good. I'll give it a bit more time for everyone to join, so that, yeah, maybe like 30 seconds. All right, I think that should do it. So I'm going to start the game. I'll give like another 20 seconds-ish so everyone can finish up roughly. Alright, maybe like 5 more seconds. Alright, just finish up your attempts. We're gonna end it. Very good. To these people, I think they got full marks. Very good. Yep. Okay. So, oh wow. It's funny, right? Because like in term 2, I'd run this class, and every single time people were like, "Oh, bro, like, I'm dying." Like it was so skewed to the right here, but like it seems like everyone's having a great time here, so that's good. All right, so yeah, the types of pulleys. There's fixed and moving. Just be careful with the words because for fixed, pinned, and roller, those are for supports, right? And arguably they're for connections as well. Or maybe these words are better suited for connections, so yeah. But fixed and moving, there's only 2 types of pulleys, right? What's the mechanical advantage of this pulley? So this is a pulley that's fixed, and it has like this reaction happening at this pin, but it's only got that one kind of advantage. Oh, I can see where the confusion is. Okay, it's because this is like okay, there's not 2 ropes, there's only 1 rope here. This is like a different state that it was drawn in. Yeah, oops. All right, and then what's the mechanical advantage of this one? All right, here's the way you think of it. Hopefully everyone can see this. Oh, so I'm using a program on my computer which allows me to draw on my screen pretty much. But if we take a free body diagram cut here, right? Essentially, there's your weight, and we're analyzing these to be all the same rope, right? Yep. So 4 times mechanical advantage. 4 to 1, I think it's cool. Okay. Yep. And the spring constant is a measure of material stiffness. Yeah, these other words, they don't quite make sense, pretty much. Yeah. And then for friction, friction removes energy from the system. We'll see that in the final question that I'm going to do. By the way, for the questions, I'm going to do them 3, 4, and then 2. 2 is actually the hardest. I realized as I was doing it. So we'll do that at the end because then you'll get an understanding from the other questions. All right. Basically, I'm going to show the QR code. Let me know if this works. I just set it up, so I didn't have a chance to check on my phone whether it actually brought me to the right page. But yeah, we're on break. We'll come back at 7 pretty much. 5 minutes or so. Check the chat quickly. Was the attendance taken? Well, here it is now. Is mechanical advantage in this course? So mechanical advantage only for pulleys is in this course because it's something that you don't explicitly learn about, but yeah, you might be like, why is there twice the amount of tension? Yeah, usually it's pretty simple though. It's not that complicated. But yeah, anyway. So QR code again. All right, might go back into it because we've got quite a bit to explain in these questions. What does it say? Attendance 6. Let me check. I think it just says attendance 6, but I didn't change the name for it, so I'm suspecting. Should be the right one, but yeah, no, it should be the right one because the old one would have closed. So you should be signing the right one. I mean, I'll just change the heading. Yeah, after the class, but yeah. Okay. All right. So here we are. Back to here. All right, so here's our question. So it says that we have a 7 kilogram collar, which I guess is another word for slider, with negligible friction, right? And it moves up and down this vertical shaft. And when the collar is released from the bottom, right? So that's important information. Released at rest, right? It moves up the shaft with a constant force of 200 newtons. Okay. And then we want to calculate the spring stiffness, which we're not given. Okay. And okay, so here it says the maximum compression is to be limited to 75 mil, and what that means is it's K up here, so that's unknown. What it means is the compression in the spring can only be compressed 75 max, right? So what I like to do is I like to draw where the second state is for the slider, just so I can better visualize it. Because what happens is once we get here, okay, do you see where this pulley, yeah, it just happens to be that where like when the string is like horizontal, right? That's the height that we're given from the center of the slider. Right? So that will be our second state, which I'll call 2. And I'll call this original state 1. Okay. And yeah. And so that happens to also be 75 here. Right? Okay, let's talk about this part a bit more for a second, right? Based on what I told you earlier. Pretty much x2 or change in length, sorry, the deformation at state 2 of the spring, right? Think of it like this. We can think of it as the amount the spring is in the end minus the original length. However, we're not given the original length of the spring, right? But we do know that the second one, like we're given the information that the second one is the original length minus 75 mil, right? So this is a really roundabout way of just saying this cancels out with this, and x2 is negative 0.0075 meters, right? That's one way you can think of it. But the other way is you can just skip straight to saying this, right? And that's just saying that the maximum compression is negative 75 mil, right? Yeah, so I've just gone the long way around. If you want to think about it based on the formula, that's how it works out, right? Okay. So the first thing we wanted to look at is the geometry of the rope, right? The geometry of this rope. So what I'm saying here is at state 1, that's where we're at right now, the rope will look something like this. But here's the pulley. And here's our collar, they call it. Right? So because L and X and S are all used, right? I'm going to call this R. I guess technically I can call this D as well. Maybe I'll call this D. Right? And we know that based on the question, the geometry, we're given these lengths. But this is simply just Pythagoras, right? This D is going to be this. Which is 0.503 meters, right? So we've just calculated the length of that part of the rope, right? So next, if we analyze state 2, it'll look something like this, right, as we said before. And the rope is simply 0.225 meters, right? That's just when the slide is there, right? And so, okay, I'm going to write this really long sentence. Okay. So the change in rope length between slider A and pulley B, what I mean by slider A is this slider here, and pulley B, right? That's this length, right? And then it's this length. That change is going to be the final one. Minus the initial, right? So it actually got shorter, right? And we know that based on geometry, right? But why I had such a long sentence to describe what I was talking about is because in the formula I mentioned earlier, S for your work part of the equation is going to be the rope that's been moved, okay? Which is literally what we just calculated, but it's been extended, right? So it has an increase in length instead, right? Rather than a minus. So that's what we're going to be plugging into our equation, right? So yeah, basically as it shortens here, this rope will end up like, so if it started here, this part will get longer, right? Yeah. Okay. Does anyone have questions so far? Check. What is S? So, good question. So S is like, it just means displacement, right? Displacement from 1 to 2. But in this question in particular, the displacement is talking about the amount of rope which has been moved. Okay, so if this is S1, right, and then it gets extended, right, that's S2. When I say S, I'm referring to delta S technically, right? So S from 1 to 2. And it's the rope which gets moved. Okay, so next we're going to, so we've basically, I would say like in most questions, the hardest part that you have to like pre-calculate is your spring displacements, right? The spring deformation, I think I called it, and S, your displacement. Those will actually take some thinking before you plug it straight into the equation. So, but once we have those, we can simply do this. Sorry, work from 1 to 2. It's delta T plus delta VG delta VE, right? Okay, I'm going to write down all the formulas for these first. Oh, I kind of lied. So H is sometimes something you have to think about. In this particular instance, since we're going straight up and down, H isn't too hard to calculate, or the change in height. But if you're going diagonally, right, you might need to consider, yeah, like your angles with sine and cosine and stuff like that as well. Okay, so let's look at these things one by one. So the force was given to us in the question, and that was 200 newtons. We want to keep everything in terms of newtons, newtons and joules pretty much, right? Sorry, newtons, meters, and joules, right? So standard SI units. Yeah, right. And so our displacement, we calculated just above. That's all good, right? Actually, before I put an M, the question said, the collar is released from rest, right? So you can imagine that the velocity, the initial velocity at state 1 is 0, but a lot of these questions will say something like this, where the maximum compression will be limited to 75 millimeters or whatever, however it's worded. But you just have to think about when the spring, like at the instance that the spring is fully compressed, the slide is not moving anymore, right? So there's actually a hidden bit of information there, which is that the final velocity is also going to be 0, right? As well as when it starts up. So it's released from rest, and then the final state that we're analyzing is also going to be at rest, or like, yeah, it's not going to be moving, right? The mass was given as 7 kilograms. Gravity is 9.81. Okay, I'm going to talk about this in a second, but my rule of thumb is you have a positive value for acceleration due to gravity. I'll explain why in a bit, but for a change in height, okay, let's look at this, right? So change in height is going to be increasing pretty much, right? So you're going to go from here to up here, and we know that number is just 0.45 meters. Okay. So this formula, right? Depending on how you want to look at it for gravitational potential energy, you can look at it like that or like that. But as long as your numbers work out the way that they should, like in theory, it's fine. What I like to do is I like to stick to this formula, and you add it, and I keep gravity as a positive number. And the reason for that is, okay, so imagine you have like a rock or something on the top of a cliff and the rock at the bottom of a cliff. Which one has more gravitational potential energy? The one at the top, right? So gravitational potential energy like has to be a bigger number for the higher one, and has to be a smaller number for the lower one, right? That's just what the definition of gravitational potential energy is, right? And so what we've done, since we're increasing our slider upwards, is no matter what, this portion of the equation has to be an increase in energy, right? Increase in gravitational potential energy. So I don't mind if you use this formula or the one below, as long as it works in your head. And for me, instead of doing double negatives, I just do positive. It just makes more sense, right? Okay, so that's that part of the equation. And then K is what we don't know, so that's our unknown. And we've worked out, well, basically x2 we worked out, right, was the compression or the deformation in state 2. And x1, basically in state 1, the spring is unstretched. It's not deformed at all. Yeah, nothing's touching it pretty much, right? So it's a 0. Anyway, so I've gone pretty slow with explaining all those things, but I'll show you how the maths works out. So that portion for kinetic energy was 0, right? This portion here equal to this. This one is equal to this, right? And because our negative number for compression is being squared, right, and the second part of it was 0, then this turns out to be a positive number, right, because it's a negative number squared. And you'll find that K is this. You can leave it in newtons per meter, or you can do kilonewtons per meter. It's up to you. I would leave it in newtons per meter because that's standard SI units, but you'll see that sometimes they give you the K in these questions, like K is 1.6 kilonewtons per meter or something like that. That's just like an extra hurdle you have to jump through in terms of the questions, but yeah, it's just like a convention thing, I guess. I don't know. Yeah. Anyone have any questions? Check online. Yep, it's displacement. Cool. Okay, here's question 4. Right, I'll do question 2 at the end. Question 2 is cooked. So question 4 looks something like this. Okay. Maybe I should have. Oh, actually, no, that's fine. Okay, so basically, yeah, the question looks like this. I've just decided to draw it. I probably should have pasted the original image. It would have made a bit more sense. But state 2 is where the spring has been stretched like that, right? And that's like all the geometry here as well. We have this pulley, fixed pulley, and this force P that's pulling on it, right? And we're given that the velocity in state 2 is 0.8 meters per second, okay? And we're given that it starts from rest, so V1 is 0 meters per second. We're also given the unstretched spring length, okay? And that state 1, it's unstretched pretty much. So it starts unstretched and then, yeah, there's a tensile force pulling it, right? Oh, and we're given the spring constant, yeah. Okay, so let's talk about the rope movement. S, right? So pretty much, yeah, okay. So S1 is yeah, basically what S is this is S1. S1 is the length of the rope from the slider to the pulley, okay? And S2 is going to be this one, which is the length of the rope from the slider to the pulley at state 2. Okay. So S1, we use Pythagoras. I'll do it in millimeters for now and then convert it. Right? And this makes sense because the length of the rope has shortened, right? As we're moving from 1 to 2. But we use Pythagoras because it's still that diagonal length, right? We're looking at that and that, those dimensions for state 1, and we're looking at these dimensions for state 2, right? Oops. The change in length, right? Technically, yeah, the change of length between what I've considered S1 and S2, right, is this. But again, that's not what I consider S, right? Because we're thinking about the other perspective. We're thinking about S being this one. S is how much the length, how much the rope moves, right, when we're pulling it. which is the opposite. So that's S. So that's what we're going to plug into our work equation, right? Okay. So the work from 1 to 2 is equal to delta T plus Vg plus delta VE, right? So pretty much in this question, we don't know what P is, right? We don't know what the force is. So it's going to be P out displacement. Actually, how much of this should I be skipping? P times S. Write out our formulas every single time. Okay. All right. Go through this one by one. So one thing which I want to look at is H. So because everything's angled, unlike before, our change in gravitational potential energy isn't going to be like an easy number. So instead, before we had something which looked like that, right? Which will still be the case, but we basically need to use our angles to find it out. And so what we do know, I'll draw a little triangle over here, is that this is delta H, and from here to here, that's given us 200, right, millimeters, 0.2, and yeah, we're not given the horizontal, but we are given the angle. So that angle here is 15 degrees. So delta H is going to be 0.2 sine 15, right? Yeah, I'll leave that as is for now and plug that in. Yeah, sure. Okay, and then S we calculated earlier. M it's given us 0.5. Right, let's look at the velocity, right? So actually no, it's not that hard. We're just given it, right? And it started from rest, so that's a 0. Mass, gravity, it's positive, right? And then K is given 250. Okay, so here we decided to write these as part of the equation instead of doing it earlier. So let's think about it, right? So your unstretched spring length, 200 mil. What this translates to is LO is 0.2 meters, right? That's what they're saying pretty much, right? And if we remember our formula, it's like this, where we know this is 0.2, right? So in the original state, the length of the spring is 250 mil, right? L1 is 250, right? But in the stretched version, it's 250 plus 200. So that's L2 for our second case, right? So now we've plugged in everything and we just rearrange for P. Then we get P. So it's basically you just move S divided by everything else I can see people still copying it down, so I'll just leave it for a second. Does anyone have questions in person? Otherwise, I'm going to tab online. If there's no rope in the question, then how would we calculate S? Let me just check the next question. Okay. I will answer this question as I'm going because it's easier to just show you examples. Yep, I'll answer that in a second. So is unstretched spring 250 or 200? Basically, the unstretched spring I see what you mean. Did I write this question down right? I think I know what this means. Okay. I think I might have copied this question down wrong. Because maybe the string isn't stretched at all. Isn't unstretched. Because then the maths would work out, and because I've got the answers right. So maybe we'll just say that that's not the same thing. So the unstretched spring length would be LO is 0.2. Yeah, and the state one it was at this amount. I think, yeah. Okay. Thank you for pointing that out. Let me check the chat again. Yeah. Okay. Maybe the question's just wrong. I don't know. Okay. So I'll move on to this example, right? And we're going to be spending a good amount of time on this one, right? So this is our last example for today, but here's where we don't have a rope, right? And when we don't have a rope, it can mean a few things, but yeah. So basically, what were we even using the rope for, right? In our equation. We were using the rope for the work part of the equation, right? And specifically, yeah, the rope, that's the amount of force on the rope, and that's the displacement of the rope. But we only really use the work equation for one other case, which is friction, which is what's going on in this question, because we have a friction coefficient now, so we have to account for friction. So when we don't use rope, we'll see how we use displacement in this case. Otherwise, if the question doesn't have rope and it doesn't have friction, then this side of the equation will probably be 0, right? That's when everything's only kinetic energy, gravitational potential energy, and spring potential energy. Okay, so we have this 2 kilogram collar, which is released from rest, right? At A, and it slides down this rod, and yeah, we know that the coefficient for kinetic friction is 0.2. All right. Part A of the question asks for the velocity of the collar as it strikes the spring. Okay. I will do blue. And part B is the maximum deflection of the spring. Okay. So here we have to realize that part A and part B of the question are asking for 2 different states, actually. So here's what I mean. So as the collar strikes the spring means here. So before the spring is compressed at all. So this would be point B, right? And the maximum deflection of the spring is basically when the spring's fully compressed like that. So that would look different as well. So let's see. That's when the spring's all fully compressed like that. Okay. So where do we start with this when we have friction involved and no rope, for example, right? Well, how do we calculate friction? We need the normal force, right? That means we have to draw a free body diagram and work out the normal force. We have gravity. We have the normal force going this way because the slide is free to slide this way, right? And we have friction. So, as per what we were talking about last lesson, you want to think about where you're taking the sum of the forces. Because if you take the sum of the forces in the vertical direction here, for example, you're going to run into problems. You're going to run into these two unknowns, right? The good news about friction and normal force is they're always perpendicular to each other, right? And so that means that we can always split it up like this. Sum of the normal forces, right? Or sum of the forces in the normal direction is 0 because it's not accelerating that way, right? So now it's equal to 0. And now we just have to account for this component here, right? Oh, sorry. Yeah, we can do that angle, sure. Okay, so we're given that angle 60, right? So let's quickly do a Z angle drawing. MG is directly downwards, right? So this is 30 degrees, right? And so this is mg sine 30, where m was 2 kilograms, g is 9.81, and sine 30 is 0.5, right? Now I've worked out the normal force, right? Yeah. Okay, so basically this slider, if you think about it, it's going to be accelerating that way, right? It's going to be accelerating that way. So if we do take the sum of the forces in the tangential direction, it will equal ma, which will equal, you know, that, some portion of, yeah, it doesn't really matter, right? The point is, we don't need to do that because we can just calculate this through this equation. Because our kinetic friction force is going to be constant, right? Yeah, and like we don't care what the acceleration is in this for these kinetic work energy equations, right? So that is 0.4, and that is what we worked out. Sure. So that is negative. Oh. Okay, well, what I'll do is I'll just have the magnitude here. So that's the magnitude of friction, right? But we know the arrow is acting opposite to the direction of motion, right? So now we're ready. Let's use our Holy Grail equation. Yeah, so here I've done it differently. So instead of denoting everything as like state 1, 2, and 3, I've decided to just do A, B, C. You can use either. So here I'm going from A to B. Okay, so from A to B, right, it hasn't touched the spring yet, right? So there's no change in spring energy, right? So that's 0. This one is going to be Fk, S, right? Okay. So Fk, basically you can think of it in 2 ways. You can do the magnitude, right? Like this. But if you do the magnitude, for friction, it's removing energy from the system. So you always have to include your negative, right? You can include it there if you want. And for S, right? S is a lot easier because I usually give it to you for friction questions. So that's S there. S is the displacement which is acting, which kinetic friction is acting over, right? So 1.5, okay. M was 0.5, right? No, M was 2, sorry. That last question. It started from rest, right? So VA is 0. This was 2. This is 9.81. Okay, let's think about H. So I'm going to consider here the datum, for example, right? So here's going to be our change in height. All right, I've got a question for you. Does it matter if I consider here the datum or here? Right. It doesn't really matter because the change in height is the same, right? So the equation goes like this. Right? So all that matters is the change in height, not like the literal numbers of each one. So you can consider the datum wherever you want. So I've decided to do it at the tips of the arrow because, I don't know, it's just easier to look at. So that's just where they drew it. So let's calculate it. Keeping in mind this angle here. Well, technically, I mean, this angle here was 60, right? So I'm just going to draw this one as 30. Cos because it's the adjacent side. So yeah, it's moved down 0.433 meters pretty much, right? In other words, it's decreased its gravitational potential energy, right? So you'll know you've done that part right if you got a negative number, right, for the energy there. Okay, let's just plug this in. So these 2's cancel out, right? It's VB squared. That's what all this turns out to be. Right? Solve for VB. 2.556. That's VB. Okay. Gets even better. So that was the first part of the question, right? Because the second part of the question is like, let C be when the spring reaches max compression. Wait, I'm going to quickly check for questions online. I'll get back to you, Mohammed, about the previous question because I have to check whether I wrote down the question right. Yeah, I'll answer this later. Okay. Okay, so all right, so the second part is the maximum deflection of the spring, yeah? So, yeah, I'm gonna do everything based on S, right? So you can do it based on S, which is going to be the displacement, or you can do it based on, I think in the answers they do, which one do they do? They do this pretty much, right? So they call this delta x, I think. So they do everything relative to delta x, but we're going to do everything relative to s. And then subtract off however much for the maximum compression of the spring. So delta x would have been the maximum compression of the spring. Anyway, so okay, we're going to set our datum here. Change in height, it's going to be 0.5, oh sorry, my bad, that's S, right? So cos 30, same reason as before. Yeah. Okay, and regarding the compression of the spring, max compression of the spring, that'll be this, right? So instead of calling it delta x, because I want everything with the same variable name, so that we can solve for one unknown, we have to look at the geometry, right? So this is S, right? This is 0.5, and so that bit here is going to be S minus 0.5, right? Yeah. And one more thing to note is our velocity, right? So at A, our velocity started at 0, right, from rest. And then we're doing one of those questions where it's to do with reaching maximum compression, right? So the velocity will end at 0 as well before the spring bounces it back up, right? And so our change in kinetic energy will just be 0 joules, right? The kinetic portion of that equation. Yeah, so we'll see that in action here. So going from A to C here. Yeah, that bit will be 0 pretty much. That's what I was trying to say. Just write this through. Let's see. Right. Like that. Oops. Okay. So we calculated FK before. That was in part 1. We don't know S, right? S is the total displacement. So that's what we're going to be solving for. M was 2, gravity was this. So H is also going to be an expression in terms of S, right? So it's a decrease in gravitational potential energy. Right? So it'd be a negative. K is going to be 1600. That's given. Don't put it as 1.6. Make sure to convert it to newtons and meters. Okay. So for XC and XA, right? So, okay, firstly, XA. XA was a spring compression over here, which was nothing, right? So we can just straight up eliminate that one. For XC, right, so down here, let's remember our equation. It was LC minus the initial, the initial, right? Wait a minute. Sorry, give me a sec. Okay, sorry, my bad. So if you do it this way, right, we're going to have the same problem as we did in question 1, which was that we don't know LO, right? But we do know that this one is the original minus yeah, whatever, max compression pretty much, right? Max compression would be delta X, right? But we call delta X this, right? So that's a very long-winded way of saying just cancel these out. And yeah, you'll find that this is equal to S minus 0.5. Let me show that geometrically. That's this here, right? That's the max compression, right? Yeah. Sorry, that was a bad explanation there. But yeah, anyway, so that's the situation. And for compression, technically this would be in minus, I realize. But since it's being squared, yeah, that won't matter. It's all right. Yeah, I don't know. It's not going to include that minus there. Okay, so let's simplify everything. I'm going to put a bracket around these S's because I can't distinguish my own writing from the S and the 5. Yes, okay. What I'm going to do is I'm going to move... Okay, this, you see what this looks like? This looks like the quadratic equation coming up. And so we're going to move everything to the right-hand side. I'm going to expand out this bracket. Simplify. Right. Plug this into quadratic equation. We get that S is equal to 2 numbers, okay? So if you did it the other way, in terms of delta X, you'll get a negative number and a positive number. Wait, actually, wait, ignore what I just said. We're doing it in terms of S, so I don't want to confuse everyone. All right, so basically we're given that S could be this or this, right? Which are both positive numbers, right? But we know that this distance here, right, which was the displacement from A to B, right, when we were looking at point B before, That was 0.5. So it has to be bigger than 0.5, right? So it has to be that one on the left. Anyway, so the max deflection of the spring is, we plug in that number minus 0.5 meters from before. We're left with this, which is the answer. We can call this delta x if you want. Yep. Okay, cool. That brings us to the end of the tute. Yeah, if you have questions, I'll be sticking around. Otherwise, free to go as usual. Let's check if there's questions online. I think everyone's good. Okay. Anyway, have a good day, everyone.